Hello everyone, dosto. How are you today? And today will be solving PYQs of communication systems. And friends, if you are able to attend this session completely, you will be able to understand that what type of questions GATE is asking, and generally, mainly concepts are repeating. So we'll try to solve some major type of PYQ of communication systems. So let's start. First of all of you are requested to mark your attendance so that we can start the session. Okay, so how many of you are present, dosto? Okay, so let's start the session, and we'll be solving some PYQs of communication systems, and we hope that the same concepts will repeat in the final GATE exam. Okay, so let's start. So we'll be solving the PYQs of all the topics, and our focus will be on the difficult or the major repetitive type of PYQs that are asked in the exam. Okay, so we'll be solving the PYQs. We will understand the concept. We will also try to understand the method to solve the GATE questions. Okay, the method to solve the GATE questions. So this will be the motive of this session. Okay, so let's start. So this is question number 1, dosto. Okay, this is the input. It is given that modulated signal is mt cos of 2 pi fct. Okay, the message signal is 4 cos of 1000 pi t, and the carrier frequency is 1 megahertz. Okay, so we multiply xt with this signal, and we pass it to a low pass filter which has a cutoff frequency of 510 hertz. We have to find out what will be the output. Okay, now obviously when the low pass filter is of 510 hertz, the output will have frequency from 0 to 510 hertz only. 510 hertz can be multiplied by 2 pi, so it will be 0 to 1020 pi radian per second. Okay, so the maximum frequency can be 1020. Okay, so let's try to solve. Okay, so the input message is also given, xt is also given, so we can see that xt will be equal to mt multiplied by cos 2 pi fct. mt is 4 cos of 1000 pi t, cos 2 pi fct. Okay, now if we multiply them, we'll get 2 cos of 2 pi fc plus 500 to cos of 2 pi fc minus 500t. This is the xt signal. Okay. Now we multiply xt with this signal cos 2 pi fc plus 40t. So if we multiply xt by simple cos multiplication, so we multiply xt with this cosine wave. So now let's see. When we multiply this cosine wave with this, obviously the frequencies will add and subtract. This 2 will go because 2 cos A cos B is cos A plus B plus cos A minus B. So this will become cos of 2 pi fc plus 500 and fc plus 50. So this will become, if we add, it will become 2 fc plus 540 plus cos of, when we subtract the 2, we will get 460 into 2 pi t. Okay. Similarly, when you multiply these two, we will get cos A plus B. We will add the two frequencies, 2 fc plus 460. We will add the two, it will be minus 460. Then we will subtract the 2, it will become cos of 2 pi. When we subtract the 2, we will get 540 into. So now we can see that obviously these will be of very high frequencies because fc is there, 1 megahertz is there. This will also be very large. This will be, we can see it, this will become 920 pi t, and this will become 1080 pi t. And now since the low pass filter will be passing till 1020 pi, so we can see that a very simple question, we can see that this will not pass, this will not pass, this will not pass, only this signal will pass. Okay. So only cos of 920 pi t will pass, cos of 920 pi t will pass. So this is a very simple question. You only have to multiply the cosine waves. You only have to use the rule, that is cos A into cos B is cos A plus B plus cos A minus B. That's it. Nothing else is required in this whole question. Okay, a very simple question, but many a times some errors are committed by the students, like we see 460 is there. So many a times we can mark option A, that can lead to errors. So otherwise the question is very simple. Now let's see this question. Okay. Now we have the carrier AC cos 2 pi fct and the message MT that is 2 pi fmt. Okay. It is given that fc is very, very large, and the carrier plus message is applied to a nonlinear device. Nonlinear device relationship is also given to us. Okay. So let's try to see. Okay. So we can see that CT plus MT is applied to the nonlinear device. I will be writing only C and M, okay, for ease of analysis. So we'll get A into C plus M, B, C plus M whole square. This will be AC plus AM. Okay, this is what we get, simple calculations where A and B are constant values. Okay. Now the output of the nonlinear device is passed to the ideal band pass filter with center frequency Fc. Okay, so the band pass filter is of center frequency Fc. Now if we pass this term, we can see that this is a simple carrier term. A is a constant value, C is a carrier, so this will be at frequency Fc. This is simply a message term because it is A multiplied by message. This will be at 0 frequency. This will be carrier square. So this will be at 2 Fc because we know that cos square will be converted into cos square theta is 1 plus 1 plus cos 2 theta divided by 2. Okay, this is also message square, so this will be at 0 frequency. This is message multiplied by carrier, so message multiplied by carrier, so message will be shifted to FC frequency. So we can see that at FC frequency only this term and this term will be passed through the band pass filter. So at the output we'll get at the output of the band pass filter we get two terms, that is AC plus the second term is 2BMC. Now we can write it A. C is a carrier term, AC cos. Okay. AC is not given anywhere, na? Should be 1 only, I think. So CT is applied to the nonlinear device in the output of the nonlinear device. Okay, no. So AC cos of 2 pi FCT. So this will be A multiplied by AC cos of omega CT plus 2B. What is the message? Message is cos 2 pi FMT. And the next term is AC cos of omega CT. Now what is the requirement? The requirement is, it is desired to have the sideband power to be the half of the carrier power. Okay, that is what we need. So now we can see that dosto, in this AM signal because it has a carrier term, this is the carrier term, and this is the sideband term. Okay, so what is the carrier power? We can see that the carrier power is A into AC whole square divided by 2. What is the sideband power? First of all, we will see the term, that is 2BAC whole square, and there are two cos terms, this and this. So one cos term will give 1 by 2, another cos term will give 1 by 2. So this is the sideband power and the carrier power. What is the requirement, dosto? All of you are able to do it. I hope all of you are able to do it. So what is the carrier sideband power? So sideband power is half the carrier power. Okay, sideband power is half the carrier power. So sideband power is 2B AC whole square 1 upon 4 should be equals to 1 by 2. So now we can see that, okay, these terms will cancel each other. AC and AC will cancel each other. 2B whole square is equals to A square. We can simply remove the square both sides, and what we need? We need A upon B. So we can see that 2B is equal to A and A upon B is equals to, I hope all of you are able to do it, A upon B, that is what needed. So 2 is the correct answer. I hope all of you are able to do it. Are you able to do it, dosto? Okay, so let's move on. I hope all of you are able to do this question, this AM question. Okay, now let's see one more question, a very beautiful question. Okay, so now it is given that xt, this xt is equals to mt cos of 2400 pi t. Okay, this is the xt input. and here we can see that the amplifier output is nxt plus x square t. Okay, and this is the band pass filter that is given to us. We want that the output of the band pass filter should be equals to 10 times of xt, that is 10 times of this. That is, we want that only 10 times of xt term should go outside the band pass filter. Now let's see. So here we can see that we have to find out the maximum value of the bandwidth of the message MT. Okay, so MT is a low pass signal with bandwidth W hertz, Okay, now, so first of all, let's see. Let us say MT is a message with bandwidth W. Okay, now let's see what is YT. First of all, let's see what is XT. XT is MT cos of 2400 pi t. So YT is 10 times of XT plus x square t. Now 10 times of xt will be 10 times of mt cos of 2400 pi t plus x square t. X square t will be m square t. Now we can simply solve this cos square term. Plus m square t and cos square t will be m square t 1 plus cos of 4800 pi t divided by 2. So here we can see that we have many terms, and this is your xt term, right? We want a band pass filter that should give us this term, and it should neglect the term which is shown here. Now we can see that, dosto, when xt has bandwidth W, then x square t, m square t, when mt has bandwidth W, not xt, mt has bandwidth W, then m square t will have bandwidth that will be 2W, right? It will be something like this. This will be the Fourier transform of m square t. Now, if we draw the Fourier transform of this term, the yt term, we can see that yt has 10 mt into cos 2 pi f cos 2400 pi t. So it has, this term has m omega shifted, and m omega shifted by 1200 right and 1200 left. So we can see that what will be the Fourier transform of y omega? First of all, we'll have, I'll draw only the right side. We'll have a triangle that will be at 1200. We take the axis as f axis, the frequency axis. Okay. Okay. So this is 1200. Plus W. 1200 minus W. Okay. Now, so this term is drawn. Okay. This is 10 mt cos of 2 pi 2400 pi t. Sorry. So we have drawn m omega at 1200 hertz. Now let's see this term. This term is m square t multiplied by 1. So it will have a m omega Fourier transform at origin. This term will be 2w, right? And similarly, m square t will be multiplied by cos of 4800 pi t. So m square Fourier transform will be present at 2400 Hertz also, because m square t multiplied by cos of 4800 pi t. So m square t Fourier transform will be shifted to 2400 Hertz like this, and this will be 2400 plus 2w. This will be 2400 minus 2w. Now we want to take out this term only. Okay, we want this term only. Now we want to apply the bandpass filter that will pass from 700 to 1700, and we want only this 10xt term. So we will apply a bandpass filter from 700 to 1700, and we want only this term. So how can we get this term? The only simple funda is, this is possible only when 1700 is greater than 1200 plus w. That is, this location is greater than this location, so that the triangle is not truncated. So we can see that w should be less than 500. Condition number 1. Now since we want only this triangle to pass, we do not want any of this portion to pass. Okay, so this is possible only when 2400 minus 2w is greater than 1700, so that no portion of this figure is passed through the bandpass filter. Okay, so we want that 2400 minus 2w should be greater than 1700. So 2w should be less than 700 and w should be less than 350. So we can see that there are two conditions. Similar conditions we can find from here also. And what is the limiting condition? One condition says that w should be less than 500. Another condition says that w should be less than 350. So we will take the condition which is more stringent. So we see that w should be less than 350, and the maximum value of w is 350. Okay, so w, the maximum value of w is 350. Okay, I hope all of you are able to do it. Okay, I hope all of you are able to do it. There is no problem in this. Now okay, so let's move on. I hope all of you are able to do it. Now let's see this question. This is a very simple question of AM. Okay, an amplitude modulation has the output of this much. Okay, now here we can see that we have three frequencies. One is at 400 pi, one is at 360 pi, and another is at 440 pi. So we can see that this will be the carrier, because this is the center frequency. This will be the lower sideband, and this will be the upper sideband. So it is given that the ratio of the total sideband power to the total power is 1 by 9. Okay, the carrier power is 50. So we can see that from here we can see that the carrier power, that is A square by 2, resistance is also 1 ohm, is 50. We can see that A will come out to be under root of 100, that is 10. Now it is given that the ratio of the total sideband power to the total power. So what is the sideband power? The power of upper sideband and lower sideband, that is B square by 2 and B square by 2. So the total sideband power will be simple B square, and the total power will be B square plus carrier power. Okay, B square plus carrier power. Actually, we don't need to find out A here. Okay, now we can see that the ratio of the total sideband power to the total power is 1 by 9. B square upon B square plus 50 is 1 by 9. 9B square is B square plus 50. Eight B square is 50. So B square is by 8 under root. Okay, B square is this. B is the root of 50 by 8. I think this is fine, dosto. All of you are able to do it. Okay, I hope all of you are able to do it. We can find out the value and we can write the answer. Okay, a very simple and beautiful question. A similar question, dosto, you can find out. This is the input given, this is the signal, AM signal given, this is the carrier, these are the sidebands. Okay, the ratio of the power of the message signal to the power of the carrier. Now here we have to find the message. Okay, we can see that this is the carrier, right? And this is the frequency upwards and this is the frequency downwards. So we can see that this will become 4 cos of 2400 pi t. We can combine these two. Okay, we can write this term as 2400 minus 400 and we can write this as 2400 plus 400. Okay, so this will become 2 cos of 400 pi t cos of 2400 pi t. So if we compare this with the original representation of AM, that is AC cos of omega CT plus MT cos of omega CT, we can see that this will become the carrier and this term will become the message. Carrier power is 4 square by 2, and here we can compare the message and get the message power as 2 square by 2. Okay, so we can find out the power of the message to the carrier. Power of the message to the carrier 2 square by 2. This will become 1 by. Okay, so these are the simple questions like these. Generally in GATE exam, if we go through the AM and FM part or the angle modulation, amplitude modulation part, then the questions are very simple and we can score marks in this section very easily. Okay, let's see some more questions. This is the question of angle modulation. So SPM and SFM are defined below are the phase modulated and the frequency modulated waveforms. This is the PM signal. Equation is also given to us. This is the FM signal. Okay. Now Kp is the phase deviation constant. Just we see the unit also. Radian per volt, and Kf is radian per second per volt. Okay. If the highest instantaneous frequencies are same, then we have to find out the ratio. The highest instantaneous frequencies, okay, are same in both. These are the type of questions of FM and PM which are very popular. So let's see how to solve it. Okay, so if we look at the PM signal, we know that the phase term is 1000 pi t plus kpmt. Okay, we can see that the instantaneous frequency is 1 upon 2 pi d phi by dt. So if we simply put 2 pi in the denominator, differentiate this, we'll get 500 plus kp upon 2 pi m dash t. Okay, now to find out the maximum instantaneous frequency, this is a constant value, we have to maximize this term. So this will become 500 plus kp upon 2 pi m dash t maximum. So derivative of mt ka maxima we need. Now similarly, here we can start with the phase term. Okay, it is 1000 pi t . Okay, now the instantaneous frequency will be differentiating with 2 pi division. This will be again 500 plus kf upon 2 pi mt. Okay, I hope all of you are able to do it. चलिए, so we have solved this question till here. Now we can see that what will be Fi maximum value, Fi max 500 plus f upon 2 pi P max. This is what we have. Now we have the message, we have everything available. So now we will solve the question. It's a very beautiful and important question. Okay, so we can see that the axis is in seconds. The axis is in seconds, right? So here we can see that what will be m dash t. So in this case, it is from 1 to 3, it is rising by 10. So here the m dash t or the slope will be, width is 2, height is 10, so it will be 5. Here the m dash t will be 0, and here the m dash t from 6 to 7 is falling from 10 to 0, the slope is minus. So now we have to find out the maximum value. So we will be in the maximum value of m dash t, that is 5. We can see that Fi max in case of Pm is 500 plus Kp upon 2 pi, m dash t max is 5. And here we can see that in case of Fm, (500) plus Kf upon 2 pi into Mt max. What is Mt max? That is 10. Straightforward. 10 Kf upon 2. Now, since it is given that these values Fi max of Fm and are equal, so obviously these terms have to be equal, right? So 5 Kp upon 2 pi equal to upon 2 pi. You can simply cancel these values, and we can say that we want Kp upon Kf, Kp upon Kf 2. Okay, I hope all of you are able to get this result. Okay, now let's start doing this question. This is also very simple 2051 marker problem. The message signal M is given, that is cosine of 2 pi fmt. Okay, and yt is also given, that is AC cos of this. We want to find out the bandwidth of yt. Now here we can see that yt is AC cos of pi fct plus mt. Mt is m. Now this is a case of single tone modulation, right? This is the case of single tone modulation. Now, since this is a case of single tone modulation, we know that the term which is with sine or cosine inside this, or the term with the message term inside the bracket, that is beta. So here we can see that this will become the beta, or we can solve it directly without any prior knowledge. We can say that the phi is pi fct plus am sine of omega m. Now d phi by dt divided by 2 pi, we'll get the instantaneous frequency, that is fc plus m upon 2 pi So here we can see that this will be your delta f. Okay. Now we have to talk about the bandwidth. This is your delta f. So the bandwidth of the angle modulation, whether it is FM, whether it is, doesn't matter. That is simply 2 times of delta f plus message bandwidth. that is 2 times of, what is delta f? Delta f is am omega m upon 2 pi plus fm. We can see that the bandwidth is dependent on the amplitude, it is dependent on fm also. So it is dependent on both the terms. So it is dependent on am as well as fm. ठीक है ना, on both, depends on both. So C is the correct answer. Very simple question. I hope all of you are able to do it. Now let's see this question. This is a very beautiful question. GATE 2023 2-marker problem. So let's try to get it. So if we focus on this AM and FM part, we can easily get 4 marks. Okay. Your A cos is the term that is given. Okay, it is passed through a nonlinear system, and the nonlinear system output is this. Let's say the term inside this is theta for ease of writing. So here we can see that yt is times of A cos theta plus 5 A cos theta whole square. Cos square theta. So cos square theta is actually, we can write it like this, 1 plus ठीक है ना. So we can see that this is what we have. Now the BT denotes the FM bandwidth. This is the message. It is passed through a nonlinear system with output of this. Okay, let BT denote the FM bandwidth. The minimum value of FC required to recover XT from YT. Okay, we want to recover XT. Okay, we want to recover XT. We want to recover this term only. We want to recover this term. Now this term can be recovered only when we can see that a very beautiful thing that we'll see. So we can see that here we have two terms, A cos theta. Obviously this will be at the center frequency or the carrier frequency FC. This will have the bandwidth of BT that is given. Okay, it will have the bandwidth of BT. Okay, that is given to us. This is a simple FM signal. Now the another signal that we have is second term, 5a square by 2. Now when we multiply the term inside the cosine by 2, we can see that this will be present at 2 FC, at the 2 carrier frequency. What will be the bandwidth of this? Now here dosto, when we multiply all the terms inside the cos by 2, the beta will multiply it by 2, but the message bandwidth will remain the same. Okay, so we cannot say that the bandwidth will multiply it by 2 directly. Okay, because we can see that the BT will be equals to 2 times of the message bandwidth. Message bandwidth is W, that is given to us, to beta plus 1. That is 2W beta plus 2W. Here the BT will be, the message bandwidth will remain the same, but beta will become 2 times. That is 4W beta plus 2W. This will be the new transmission bandwidth. So we can see that this is actually 2 times of BT minus W. 2 times of BT minus 2W. Okay. Now, what should be the relationship? What should be the carrier frequency? This is a very beautiful question. Let's try to answer. So here, the first term is at FC. Okay, the first term is at FC, and the bandwidth is calculated both sides. Okay, right side as well as left side. Or we can talk of the swing. We can talk of the swing. We can talk about the swing also. Okay, so we look at the bandwidth, one-sided bandwidth. The one-sided bandwidth will be W beta plus W. Okay, and the next or the another one is at 2FC. Okay, what will be the the one-sided bandwidth? So the two-sided bandwidth will be 2BT minus 2W. Okay, 2BT minus 2W, or we can write it like this. The one-sided bandwidth will be BT by 2. Okay, what will be this, dosto? One-sided bandwidth. So this is the total bandwidth, two-sided. What will be the one-sided? BT minus W. Okay, now we know that the total gap between these two, that is FC. So we want that the gap FC should be greater than this whole gap. So FC should be greater than the total gap available, that is BT by 2 plus BT minus. FC should be greater than BT by 2 minus. This is a kind of relationship that you need to find out the answer. Okay. Okay. Now, if we assume that W is negligible, like W is very small, the message bandwidth is very small as compared to the frequency deviation, we can neglect this term if you want to, and we can see that C will be the correct answer. Okay, I hope all of you are able to see this. Now let's see this question, dosto. The baseband signal MT shown in the figure, this is the message signal that is given to. Okay, we can see that the time axis is in milliseconds. The PM signal is given to us. Okay, the time axis is millisecond, as we can see. Okay, so we can see that we have to find out if the carrier frequency is 50 kilohertz, okay, and K value is also given, then the ratio of minimum instantaneous frequency to maximum instantaneous frequency. A very simple question. By simple analysis we can get the answer. Let's try to do. We can see that the phase term phi is equals to phi FCT plus MT. Now we can find out the frequency, that is 1 upon 2 pi d phi by dt. So we can easily find out the frequency, that is FC K upon 2 m dash t. Now let's find out the derivative of the message. The message is going from -1 to +1 in 1 millisecond. Then we can see that the dash t is 1000. From 1 to 3 is going from +1 to -1. So here the derivative will be negative. From 1 to -1 it is going in 2 milliseconds. So it is -1000. From -1 to +1 it is going in 1 millisecond, that is 2000 will be derivative. So here we can see that the derivative values are only 2000 and -1000. So if we look at this term, we simply put k here, fc is 50,000, so we can see that this is k is 10 pi divided by 2 pi, that is 5 dash t. Now m dash t has only two values, that is -1000 and 2000. So we can see that what is f max, that is 50k plus 5. What is message maximum value, that is 2000. I will write only, that is 60k f min k minus, that is 45k. Now we have to find out the ratio of minimum instantaneous frequency to maximum instantaneous frequency, f min f max, that is 45 upon 6, 3/4. So like this we can solve the questions very easily. I hope all of you are able to do it. Okay. This is already done. Okay. Now let's see this question, dosto. The message MT as shown in the figure is applied to both phase modulator and frequency modulator. You have to find out the ratio of Kp upon K for the same maximum phase deviation. We want that the maximum phase deviation should be same for the cases. Here also we can see that the ratio Kp upon Kf is radian per hertz. We can see that the Kp is radian per second, Kf is hertz per volt. Sorry, not radian per second, it is radian per volt. You can see that since here it is written hertz, that's why Kf is in hertz per volt. Now, case of Pm, the phase term is omega Ct plus Kpmt. Okay. Now we have to find we can see that this term will be the phase deviation term. So the deviation term is Pmt the maximum deviation will be Kp multiplied by Mt max, that is 2 times of Kp. Okay. Now we will see the Fm term. We will see the Fm. In case of Fm, we know that the phase is omega Ct plus 2 pi Kf. Now why 2 pi? Because Kf is in hertz per volt. 2 pi Kf integration of the message. Now, if we will do the running integration of this rectangular wave, when we will do the running integration of the rectangular wave, we will get a triangular wave. And what will be the triangular wave? We can see the triangular wave will be like this. The maximum value will be 4 and it will fall like this. Then it will go to 4 and then it will fall. So maximum value of this will be 4. So we can see that the running integration of will have the maximum value equal to 4. Now we can see that the phase phi will be omega ct plus 4 kf into 2 pi, okay, 4 into pi kf. So we can see that this will be the maximum phase deviation. Now we want to equate the maximum phase deviation of both the terms or both the expressions, because it is given that both the cases have maximum phase deviation equal. So we can see that 2 kp equals to 4 into pi kf. We have to find kp upon kf. We can do that. That is 4 pi. Okay, so we can see that the answer is 4 pi. I hope all of you are able to do it. Okay, so let's move on, दोस्तों. I hope all of you are able to solve the question. Now let's see some more questions. Suppose that the modulating message is given to us, okay, and the carrier signal is given to us. Which of the following is a conventional AM signal without over modulation? So conventional AM signal, but we do not want any over modulation. Okay. That the message is 2 times of cos omega m. Okay. This is not the AM signal. We can cancel it out. 1 plus mt will not give us will give us a AM signal, but this will be over modulation because mt will have 2 cos omega mt. Obviously that will give us a over modulation case. This is also wrong. Okay, if we look at this term, here we can see that this will become AC cos of omega ct plus, we can simply put the message here and we can see that this will become A by 2 cos omega mt cos omega ct. Now here if we took at AC common, AC cos omega ct common, we'll get 1 plus cos of the mt divided by 2 cos of omega ct. So here we can see that we have a 1 by 2 term here with the cosine wave, and modulation index will be 1 by 2, and thus this will be the correct answer. This is the AM signal with under modulation, that is mu is, or the modulation index is 1 by 2. Perfect. Let's solve the question. Consider the FM broadcast that employs a pre-emphasis filter. Now what is the pre-emphasis? Pre-emphasis is a high pass filter, as we all know, with the frequency response of this. The frequency response is also given, that is 1 plus j omega upon 10 to power 4. This is your h omega of the frequency response of the pre-emphasis. Now this is a 2022 2-marker problem, a very simple problem, that is of pre-emphasis and de-emphasis. we have to find out that which of the following will work as a de-emphasis. So obviously we can see that the de-emphasis will be H omega will be 1 upon SC R plus 1 upon SC. Okay, now if we solve this, we can see this will become 1 upon RSC plus 1, that is 1 upon 1 plus j omega RC. We want that the pre-emphasis and de-emphasis should actually cancel each other's effect. So de-emphasis should be simply opposite to the pre-emphasis. So we can see that we want that this should be 1 upon 1 plus j omega divided by 10 to power 4, or we can see that we want that RC should be power minus. So which option will give us the answer? Obviously this will not give us, because this is 1 and 2, so multiply will have a 2 term. This will not be the answer. 1 and 2, option A or option D can be the options. So let's see. So we can see that this is 1 kilo ohm and 0.1 micro. Obviously this can be the answer. This will not be the answer. Yes, A will be the correct answer. We can see that 1 kilo and 0.1 micro, this is 10 to power minus 4. So obviously A option is correct. We only have to see that the de-emphasis and pre-emphasis should cancel each other. So if the pre-emphasis filter is given, we can easily find out the filter response of the de-emphasis. We can compare and get the result. Okay? Okay. So let's move on. A super heterodyne receiver operates in the frequency range of 58 to 68 megahertz. Okay, so it is given that the carrier frequency hertz. Okay, the intermediate frequency is given. The intermediate frequency is given, that is, we have to choose it, and the local oscillator are chosen such that the intermediate frequency is less than the local oscillator frequency. Okay, it is required that the image should fall out of this region. The minimum intermediate frequency is. Now generally we take the case of up conversion. So in case of up conversion, we can see that the local oscillator is Fc plus Fif and image frequency is Fc plus 2 Fif. Now what do you want, dosto? We want that Fc plus 2 Fif should be outside of the range. Outside the range of 58 to 68 megahertz. Okay, so we can see that 58 plus 2 Fif should be greater than 68. 2 Fif be greater than 10. Fif should be greater than 5. So we want that the image should be outside the range which is mentioned. Okay, so minimum value of the Fif is 5 megahertz. Okay, I hope all of you are able to do it. Okay. Let's move on. Okay. So this is a very simple question, दोस्तों. Y is equals to 2x plus 3. We have to find out the relationship between the variance of y and x. A very simple question that can be solved easily. We know that y is equals to ax plus b, and in that case the variance of y is equals to a square variance of x. So if we do the comparison, we can see that a is equals to, so c will be the correct answer. A very straightforward question that can be marked very easily. So one marker problem that we can get from the random variable random process topic like this, we can solve it very easily. This is a very beautiful question, दोस्तों. 2022. U and V are two independent zero mean Gaussian random variable of variance 1 by 4 and 1 by 9. We have to find out the probability of this. Okay. Now U and V are zero mean Gaussians. Okay. We can see that this will be, can be, say that greater than equals to minus u greater than 0. Let's create a new random variable. Let's say this is the new random variable z. Z is equals to minus, the mean value of z is times of v का mean, of u का mean, that is 0. Because v and u both are zero mean Gaussians, so mean of z is 0. We can see that the variance of z will be 9 times the variance of v plus 4 times variance of u. Because they are independent, so we will not have the covariance term that we must have in 3v minus 2u expression. You can see this will come out to be 9 into 1 by 9, 4 into 1 by 4, that is, this is the variance of z that we have got. Now we have to find out the probability z greater than equals to 0. Obviously, since v and u are both Gaussian, z will also be a Gaussian. Z will also be a Gaussian. I think the looking at the strength of the students in the class might not be more than 100 minutes. Okay, so probability of z greater than equals to 0. Now since it is a Gaussian, zero mean Gaussian, since it is a zero mean Gaussian, probability z greater than 1 by 2 will be 1 by, z greater than 0 is 1 by 2. C is the correct answer. Okay, I hope all of you are able to do it. Okay, now let's see one more question. A digital communication system transmits bits. It's a very simple question, we can get the answer very easily. A digital communication system transmits a block of n bits. The probability of error in decoding a bit is alpha. The probability of error in decoding a bit is alpha. The error event of each bit is independent. Like we can have error in any bits independent. The received block is declared erroneous if at least one of its bit is decoded wrongly. So if any bit is decoded wrongly, then the whole block is erroneous. The whole block is erroneous if any one bit has error. Okay. So probability of error is 1 minus no bit error. Okay, 1 minus no bit error, that is 1 minus NC0, no bit should have error, alpha to power 0, 1 minus alpha to power n. NC0 is 1, so 1 minus the probability of error, a very simple binomial problem that we can get. N should be outside this. So 1 minus alpha to power n. I hope all of you are able to get this. Okay, I hope all of you are able to do this question. Let's move. Okay, X is a random variable with uniform distribution. In 2022 marker problem. So X is from minus to 10. Okay, X is from minus 10. Now we have to find out this probability. Now दोस्तों, you have to solve it like this. So first of all, we can see that y should be less than equals to 7. What should be the result? That is simply 2x minus 6. You can solve that. X should be less than equals to plus 6 divided by 2. What is it? That is 6.5. X should be less than 6.5. Okay, X should be less than 6.5. This X should be greater than 5. What is this probability? Greater than 5. Okay, now we can see that what is this probability? Probability y less than equals to 7, x greater than equals to 5. That is, we can say x less than 7 can be written as x less than equals to y less than 7, x less than 6.5. Given that x greater than equals to probability x less than 6.5 intersection divided by probability. Now here we can solve the result. It is from 5 to 6.5. Now for the top probability or the numerator is simply the area of this region. Now we can simply, what is the area of this region? That is equal to, width is 1.5, height is divided by 12, x greater than 5, what is the region? 5 to 10. Okay, this 5 to 10. So width is 5, height is 1 by 12. So the answer is 1.5 divided by 5. So like this we can solve the question. 1.5 divided by 5. I hope all of you are able to do it. A very beautiful question दोस्तों, that we can solve very easily. Okay, let's move. Now, for a real signal, which of the following is or are valid power spectral densities? The 2-marker question of GATE 2020. It's a real signal. It is a real signal. We want to find out which is a valid power spectral density. For a real signal, the power spectral density should be real and even. Real and even. And it should be non-negative. Means power spectral density can never go negative. It can be 0. It has to be positive. So this option is wrong. This is even. This is also even. Even is fine, but cos will go positive, negative. So this will become negative also. We don't want any negative PDFs. This is wrong because it is not even. This one is wrong because this is not even and it is negative also. Only this option is right. 2 upon 9 plus omega square. This will be positive also always, or it can go to 0, but it will never go negative. And this is the even function of omega. Even function of. Okay, let's move on to the next question. Now दोस्तों, many a times it is very important to read the question very clearly and specifically. In this question, it is given that the power spectral density of a real process xt for positive frequency. It is given that we have a real process and the PSD is of positive frequencies. Okay, we have to find out the value of expectation of x square and we have to find out the value of the mean value. That the expectation x square means the total power. Now the total power is obtained by simply 1 upon 2 pi times minus infinity to infinity power spectrum. Now since here we have only the positive portion and for the real process the power spectral density is real and even, we can say it is simply times of power spectrum. We have to find simply the area of this positive part. The area of this delta is 400. Area of the triangle is, this is, the width is 2, height is 6, half, base, height 1000. This we can say this will come out to be 6400 divided by pi. This is the total power. Now if you want to find out the average value is simply under root of the DC power. DC power means the power at 0 frequency. Okay. Now since there is no zero frequency power here, because at zero there is nothing in the power spectral density, so the under root of DC power will be 0 only. Okay, so there is no DC power. The total power expectation of x square is 6400 divided by pi. B is a correct option. It is very important to include the negative frequency part also, because positive and negative both are present in power spectral density. Okay, I hope all of you are able to see. Now let's see this question, a very beautiful question. Okay, a white Gaussian noise with zero mean and power spectral density of N0 by 2 when applied to a first order RC low pass filter produces an output NT. At a particular time t equals to tk, the variance of the random variable will be. A very simple question. I hope all of you will be able to solve this very easy. RC low pass filter. You can see that the input is a random process, that is noise. It is a zero mean. The power spectral density. Remember that N0 by 2 is in hertz. H omega will be 1 upon 1 plus j omega RC. Okay, so now we can see that the power spectral density of the output random process will be the power spectral density of the input multiplied by h f ka mod square. Okay, this is what we get. Now दोस्तों, we sample the random process, we sample the output random process, and we get a random variable. The random variable will also have mean equals to 0, right? Will be 0 of the random variable also. And the total power of the random variable, will be equal to the variance of the random process, or we can say that the total power of the random process will be equal to the variance of the random variable. Okay, the total power the random process is equals to variance random, that is minus infinity power spectral density f का 4 pi square f square r square c. We can take the things common, N0 by 2 4 pi r square c square as common. Okay, now we can see that this integration can be easily done. This will be 1 upon 4 pi we actually under root of, we know that this is a square, this is f square, so this will be a square, so it will be 1 upon a, that is 2 pi rc. This will be tan inverse integration from minus infinity to infinity, that will give us pi again, pi square rc cancel and become from n naught upon 4RC. So the power of the random process, which is same as the variance of the random variable, will be N0 by 4RC. This is the correct answer. I hope all of you are able to do it. Okay, so A is a correct answer. Like this, we can solve it very easily. Perfect. Let's move. So this is a very beautiful question of GATE 2019 2 marker problem. I think it is missing. That the random process YT is described as this. Okay. HT convolved with XT plus ZT, where XT is a white noise process with power spectral density of 5. The HT is a filter, low pass filter, minus 5 to 5 Hz, HF is 0.5, 0 elsewhere. ZT is another stationary random process which is uncorrelated with XT with power spectral density as shown below. Now, power spectral is not given. We take any figure. This is your power spectral density of Z. Okay. So now those two, it's a very simple process. I don't think anyone will have any problem in this question. It's a very simple question. YT is HT convolve XT plus ZT. So power spectral density of YT will be equals to power spectral density of X multiplied by H mod square, because HT convolve XT will have power spectral density equals to this plus power spectral. So we can see that the power spectral density of XT is a constant value because it's a white noise of value 5 watt per hertz. HF is 0.5. Okay, so it will be 5 hertz multiplied by 0.5 whole square. We get a rectangle from minus 5 to 5 of height 5 multiplied by 0. Plus the power spectral density of Z rectangle triangle by 10 minus 5 to 5. We can see that the power of the output, power of YT will be, so power spectral density is simply adding these two. Power of YT will be simply minus power spectral density YT. We can see that it is the area of these figures, that is 5 into 0.25 into half. We can simply multiply them and get the answer. This is 62.5. That. So I hope all of you are able to get these results. Okay. I hope all of you will be able to solve questions in the GATE exam. Thank you, dear students. Bye-bye and take care.